This is a pressurized tank that could be part of a hydraulic lift or any hydraulic system operating heavy machinery. The tank is sealed except for, let's say, a small hole in the side here out of which fluid is being ejected into that stream. We would like to be able to predict the speed at which water is going to come out of this tank here. We'll need to know what the pressure is inside the tank. So I've given us that, let's say a little bit above atmospheric pressure, 1.2 atmospheres, the surrounding air being at 1 atmosphere. So let's determine the speed of the water at two different points on a streamline here. Here I'm going to look at this middle streamline of that set of 5 as it passes through a gate 1 and gate 2. Gate 1 being wide compared to gate 2 here. We'll say this is a tiny hole compared to the size of this large tank. And all 5 of these streamlines pass through gate 1, but then all 5 have to squeeze through gate 2. So we know from the Bernoulli effect that we're going to have much higher speed exiting through gate 2 and a very low speed here at gate 1. Although this hole is draining the tank, we imagine the hole is so small that it drains it so slowly that there's no real change to conditions here inside the tank during the time it takes this little spout to form. All right, let's apply our continuity equation first to gate 1 and gate 2. The flow rate through gate 1 will have to match our flow rate through gate 2. So A1 V1 has to equal A2 V2. And if A2 is much, much less than A1, then our speed at 2 will have to be much, much greater than our speed at 1. There's our Bernoulli effect right there. Now let's apply the Bernoulli equation to point 1 back here in the tank, and point 2 is right there just at the opening of the tank, at the mouth of that hole where the water is contacting the surrounding air. And the key point here is that where the water contacts the surrounding air, the pressure of the water has to match the pressure of the surrounding air. So the pressure at 2 is going to have to be equal to the atmospheric pressure, 1 atmosphere. But in trying to simplify the Bernoulli equation here, we can note that if we follow this streamline here through the middle, that there is no change in z from point 1 to point 2, no change in height there. So this rho g z1 term and that rho g z2 term, those are the same, those cancel out. So with that having disappeared, we see that we're going to be exchanging pressure for speed along this particular streamline. There's no change in gravitational potential energy along that streamline. So let's start rearranging this to solve for V1, or rather solve for V2, the speed right there at the mouth of the hole. Get our pressures together on one side and get these kinetic energy density terms over on the other side. Maybe factor out the 1/2 rho from both those terms to get that expression. And here, where we've got the speed at the hole squared minus the speed back in the tank squared, here's where we note that since speed at the hole is much, much greater than the speed back in the tank, that in this difference, V1 squared is negligibly small compared to V2 squared. So we'll drop that term and then finish solving for V2 and find that it can be given by the difference in those pressures and taking the density of our fluid into account. If it's water, the density would be about 1,000 kilograms per cubic meter. So P1 minus P2, the pressure here in the tank is given as 1.2 atmospheres. P2, that's where the water contacts the surrounding air, so the pressure has to match the surrounding air, 1 atmosphere. So 1.2 minus 1 is 0.2 ATMs. We'll remember here to convert our 0.2 ATMs to newtons per square meter or pascals, since there are 10 to the 5th pascals in 1 atmosphere. we have to convert to SI units. And doing that, we find that the speed is expected to be this value where the water exits the side of the tank. We could then go back to our continuity equation, knowing speed 2, work out what speed 1 must have been. And its speed 1 is given by this ratio, multiplying speed 2. And if the size of the hole is very tiny compared to the size of the tank, then this speed is negligibly tiny compared to the speed of the spouts, and so approximately 0 here. Okay, we found that speed of our water being forced out of this pressurized tank. We see it mainly depends on the difference in pressure between inside the tank and outside the tank. And so along that streamline from point 1 to point 2, there's no change in gravitational potential energy, but we're converting some of our pressure into kinetic energy along that streamline.